In this world, the products of science function with planned efficiency. However, political and social affairs usually display all the human failings. Small wonder there's good cause to ask why science works.
The scope of science has widened progressively during the last 300 years, and in our lifetime has been increasing by leaps and bounds. Man has learned how to use the power of coal, and has found in this way the equivalent of whole armies of slaves. Man has realized the dream of humanity in learning to fly. And now we talk through time and distance. For instance, you are hearing me now across something like 6 months of time, and across a distance of perhaps 1,000 miles. What can be the secret of such unprecedented success and irresistible growth? At one time, it was thought that science would result from accumulating observations and comparing them systematically. This was the idea of Francis Bacon and even of John Stuart Mill in the 19th century. Now we know better. We have had to invent a much more powerful, sharper tool in order to bring out deeply hidden laws of nature. And this sharper tool is experimentation in the laboratory. There, experiments do not merely tell us that such and such things happen. They yield numerical relationships between physical quantities such as lengths, temperatures, voltages, what we call scientific laws. In the next step, when scientist has collected several more or less related numerical laws, he feels the need of a theory to unify them. Such a scientific theory is a construction of the imagination. For instance, suppose we have found out, as Boyle did in the 17th century, that if we have air or any other gas compressed under a piston, it takes twice as much force exerted on this piston to reduce this volume of gas to 1/2. Let us call this law A. And suppose we have found, as was done at the end of the 18th century, that if we have gas or air enclosed in a container of definite volume, such as a pressure cooker, doubling the temperature doubles the pressure. Temperature in this case is not the Fahrenheit temperature, but is measured on another appropriate scale. Let us call this numerical law, Law B. These two laws must have something to do with each other, since they connect the pressure, the volume, and the temperature of a gas. But on the other hand, consider the law established in the beginning of the 19th century by a French chemist that 2 equal volumes of hydrogen combine with 1 volume of oxygen to give us 2 volumes of water vapor or steam without any residue of hydrogen or oxygen. Let us call this law, Law C. Law C has not any immediate connection that you might guess with laws A and B. However, when we have a certain number of empirical laws like these that all have to do with gases, we begin to wonder what a gas actually consists of, whether we couldn't imagine a model of a gas which would explain in some way why a gas behaves in physics according to laws A and B, and in chemistry according to law C. One such model of a gas had been suggested by Newton. Another such model was suggested later and is called the kinetic theory of gases. Now, when we are in the presence of 2 or more theories like these, the work of the scientist's imagination, we must find some way to decide which one is the most acceptable. It usually happens that the man who has had enough imagination to invent one of these theories has invented at the same time a new experiment, some new laboratory setup, which according to his theory ought to work in such and such a way. The result of performing this experiment is thus, in the most favorable cases, a definite decision for or against his theory. In the case of laws A, B, and C about gases, a certain hypothesis was suggested at the beginning of the 19th century, which said that the number of molecules of hydrogen or oxygen in each of these boxes was the same. Although this hypothesis proved very helpful throughout the 19th century, it was still nothing but a figment of the imagination until scientists were able to measure how many molecules actually were contained in a box of a given size, such as this one, for instance, which has the standard volume of 22.4 liters. And this was the work of a French physicist, Jean Perrin, in 1908. He used several types of experiments. One in particular concerned the unceasing irregular motion of particles suspended in a liquid. Here we have a diagram made by hand of such a particle which was followed in the field of the microscope. And from time to time, every second or so, one of these particles bumped into another one, and you can see it changing its direction, just like a billiard ball who has been met by another. And this intricate path is what we actually observe in a case like this. Now, this is only one of half a dozen type of experiments from which Jean Perrin showed that we could find out this number of molecules in a given box. And all these experiments converged in giving approximately the same value for the number of molecules containing this standard box. And that was 6, followed by 23 zeros. Agreement on such a fantastically large number was most impressive. And from that moment on, the hypothesis was accepted by all scientists. And so was the theory of which it was a constituent part, the so-called kinetic theory of gases. In this way, science extended an umbrella, so to speak, over laws A, B, C, and several others which I didn't mention. Incidentally, the Newton model was found not to fit these experiments, as well as the newer model, and therefore was abandoned. After a theory has gained acceptance among scientists, it usually bears fruit for quite a while in several domains. However, exciting developments take place when observations do not fit into the reigning theory. This may happen either because the new observations actually contradict the theory or because they stand apart in some newly discovered field of science. As an example of the first case, this graph records a numerical law. Here we plotted the velocity of a particle, an electron, in fractions of the speed of light, 0, 10%, and so forth, 90%. And here we plotted the mass of the electron at a certain scale. And you can see that the mass is increasing at the same time as the velocity increases. Now, this is in direct contradiction with Newton's laws, which rested on the assumption of the unchanging mass of all particles, regardless of speed. On the other hand, a new experiment may reveal a completely new field, quite unconnected with the known ones. The discovery of natural radioactivity at the end of the last century was such a turning point. The whole of nuclear physics derived from there. Since that time, physicists have partially succeeded in including radioactivity under a broader umbrella, covering most of classical and modern physics, although one must admit that the task of unification is not yet complete. you can see that imagination plays a considerable role in pure science. It is imagination that invents the new theories and devises new experiments to test them. It also takes considerable imagination to devise new machines or new processes in the applied sciences. The work of the engineer and the applied scientist, at its best, consists in using existing, well-known laws to design a new device or a new substance with specific properties planned in advance. For instance, take the invention of numerous types of electric motors between 1860 and the present times. DC motors and AC motors, synchronous, induction motors, three-phase, and so forth. The inventor of such a motor takes for granted the laws of electricity as they have been established by Ampere and Faraday and many others. But he invents new ways of arranging the components of motors: iron cores, rotating steel drums, intricately wound coils of copper wire carrying the electric currents. Such engineers create motors which possess certain desirable properties, which enable them to perform specific jobs particularly well. For instance, to start under a heavy load, to keep constant power under different kinds of load, and so forth. Now here's another example. With the development of remotely controlled machinery, it became necessary to have some means by which a pointer on a dial at some remote place could be made to follow faithfully the motion of a pointer, recording, let us say, the temperature of a furnace. Well, this is actually done by means of a small electric motor specially designed for the purpose. Although the design of the motor is new, it would have been immediately understood by an engineer in 1900. Here's an example of such a setup. Here we have, let us say, the dial which should indicate the temperature in a furnace. And we want to have this temperature repeated in the office of the engineer, perhaps 200 or 500 feet away. Well, to that effect, we install behind this dial an electric generator of a certain type. And behind this dial, we put a motor of very similar type, and we connect the motor and generator by means of a certain type of cable. Here it is. And as I'm going to connect these two motors together, the motor and the generator, look what's going to happen. Now that I have connected, you see that this pointer points now to the same number as this one. And this is the master dial, and as the pointer, which my hand drives, moves with as the temperature of the furnace changes, well, 500 feet away, this pointer there indicates all the variations of temperature slavishly, hence the name of servo motor used for this particular type. In a similar way, an electronics engineer invents some new combination of coils and capacitors and resistors and vacuum tubes in order that the circuit he builds should have certain properties. Maybe he wishes to receive a radio wave in a certain domain of frequency with such and such precision. Moreover, the engineer's design will have to satisfy certain economic limitations. Now, for instance, from this design, where familiar components are arranged in a new way, is produced this radio set, which sells at a certain competitive price. Again, in the same way, a chemist will make use of known procedures in organic chemistry to create a new molecule. That's what we call an organic synthesis, which will have certain properties, for example, a pharmaceutical with specific clinical benefits and no deleterious effects on the patient's heart or digestion. The organic chemist has created in this way hundreds of thousands of compounds: pharmaceuticals, perfumes, dyes, plastics, synthetic fibers, and so forth. These organic compounds, which have never existed in the world before, are combinations of chains and cycles Here's a chain, and here's a cycle, combined according to well-known laws of organic chemistry. You see that this is quite similar to the design of new electric motors or radio receivers. Well, I've mentioned several times the check made on a proposed theory by laboratory experiments. Now, laboratory experiments, or at any rate the immense majority of them, are not only quantitative, but numerical. They don't only say that a quantity increases from a small to a large value. They say what this quantity is. And they consist essentially, therefore, in finding the numerical value of any physical quantity, voltage or length or what is it, measured with a certain unit. This is usually done, particularly nowadays where we have the help of electrical methods, by reading the position of a needle in front of a scale. For instance, here's a battery, and if we want to find how many volts it produces, well, I connect it to a voltmeter, and you can see the pointer moving and standing still in front of a certain division. This is what we call a pointer reading. Numerical measurement, or pointer reading, constitutes the ideal definition of what is a scientific fact. You know all the interminable discussions that there are in other fields of what constitutes a fact. Is it a fact that Caesar pronounced certain memorable words on crossing the Rubicon? Is it a fact that Elizabeth I was in love with the Earl of Essex? Is it a fact that the witness to an accident saw the victim crossing the street at such and such a time? Science makes things very easy for itself by refusing to consider facts of that type. It considers as facts only pointer readings, which moreover must be the end product of a setup in a laboratory in which all the relevant physical variables have been identified and taken care of. Some of them by having them carefully measured, and others by being completely eliminated. The result is called a scientific fact. As a result, any competent assistant asked to read the position of a pointer at the end of a certain experiment will find the same result as anyone else in the laboratory. His judgment of the coincidence of the pointer with a certain line on the scale is a judgment of fact. It is not a value judgment. Now, you know that there are value judgments in all fields of human endeavor, not only in art and in poetry, but in ethics, in religion, in government, and so forth. We cannot decide which is the best form of government without bringing in assumptions that are value judgments. For instance, some think that people are the best judges of what they need. But on the other hand, others might contend that it is the function of the state to give them what is good for them. And of course, we know that the essence of value judgments is that they are different from one person to the next. On the contrary, in science, because we don't have to make value judgments, our assistant or any other laboratory worker, as well as other scientists repeating the experiment under the same conditions in different places, will find exactly the same number. This more than compensates for the restrictions that science has placed upon itself in defining what constitutes a fact. It makes up for such narrowness as we have defined by the absolute confidence we can place on a pointer reading which has been checked by different people at different places and different times using similar equipment. Thus, our cold judgment of fact at work in the laboratory. Let us now look at the situation in everyday life, outside the laboratory. Here it is the tightest of observations that emotions perturb the judgment. Momentary and violent emotions make us incapable of using our reason to act correctly. If a man is run over by a taxi in crossing a street, a friend might say, "I'm not surprised. I had talked with him 5 minutes before, And he was so upset by the news he had just received, he just didn't know what he was doing. Such is the case for all strong emotions. Joy, love, hate, anger, fear, all disturb our judgment. Well, the remarkable thing is that by restricting itself to pointer readings, science has created a safe and closed domain where the scientist is protected against the effects of his own emotions. The coincidences of a pointer with lines on a scale are equally apparent to all observers. This is one basis of the power behind the famous quantitative method of science, the use of numbers. And here's another. Not only can you have complete confidence in the numerical data, but the fact that they are numerical is what enables science to make use of the tremendous force of mathematics. And mathematics, at a certain level, is nothing but a collection of logical formulas which enable one to give at once the conclusion of a reasoning without having to run over all the steps leading up to it. For instance, we know from the early steps of algebra that if we have the product of the sum and of the difference of two numbers, the result is the difference of the squares of those numbers, the formula we had here a minute ago. Well then, anyone who knows that formula gives the result without having to do that long multiplications. And many much more complicated operations of mathematics, let us say finding the root of a quadratic equation, are second nature to anyone who has had a good course of first-year algebra in college. So in this way, considerable time is saved and the result is obtained automatically and is preserved from the effects of the emotion. It contains no value judgments whatsoever. Now in the same way, the laboratory routines are a set of well-established rules, like the rules of algebra. And if these are followed correctly, they will lead to a specific result neatly and without errors. In a chemical laboratory, let us say, if you ask an assistant to find out which salt is in solution in this test tube, or to distill this or that mixture, he will do it in the approved way, without having to ponder about the steps of the procedure. That's exactly what his graduate training was for. In this way, imagination, and more generally the emotions, have been eliminated from the very large part of research work which is purely routine. The pointer readings, the standard laboratory procedures, the mechanical operations of mathematics. But at the highest level of scientific strategy, whether theoretical or experimental, we still count on imagination to play its irreplaceable role. Consider now, on the one hand, all that imagination contributed to the advancement of science, the invention of all the new concepts, of the new theories, of the new untried experiments, of the new laboratory procedures. And note, on the other hand, that all suggested hypotheses, no matter how crazy they seem, contradictory either to common sense or to the best established laws as we know them, those hypotheses are suggested to numerical checks, which are independent of the emotions of the observer. Then you must arrive at the conclusion that science is an extraordinary, unique domain of human activity in which we bring together the advantages of unbounded imagination on the one hand, with, on the other hand, the power of reason, applying cool and unemotional checks. No wonder that in this way we arrive at those products of the imagination, those scientific theories and procedures, which at a given moment present the most effective way of dealing with a scientific situation. Because scientific results are so solidly established, it is possible to build upon them. This is how it comes about that science is cumulative, that Newton knew so much more physics than Galileo, Maxwell so much more than Newton, and Einstein than Maxwell. Such comparison would be impossible in any field but science, and only in science do we have the quiet assurance that leading scientists in 1980 will know much more than Einstein. This is why in science we constantly have to produce new presentations which combine in a short condensed form facts which 20 years ago filled volumes. There is no end in view for that cumulative process at the present time. We have seen it at work for the last 350 years, and it is obviously still accelerating. Very likely, like every other biological or social process, it will someday reach saturation, reach a new plateau, as the psychologists say. This is certainly very, very far away from us now. If science grows like a population grows, starting from a former low level, and then slowly growing and reaching a higher level of saturation, then science is still in the expanding phase of its progress. Such is the phenomenon of the growth of science that we see around us today. I have tried to explain what causes that growth, this irresistible growth, which results from the combination of the power of the imagination and the power of reason. In other words, we have seen why science grows.
This is National Educational Television.